So today we're going to talk about optimization and the first derivative test. The first derivative test is necessary in order to understand what optimization is and how to do it per se using calculus. And then optimization, in my mind, is one of the most fundamental and useful applications of derivatives that you're ever going to encounter. And definitely the most useful in the business world and probably one of the most used. It's also used a lot on AP tests, at least the first derivative test is, because it helps you find relative minimums and maximums, really useful in curve sketching, etc., etc., etc. All in all, really nice to know. So we'll get into that. So starting with the first derivative test. The first derivative test is used to find relative or absolute minimums and maximums of any given function. Now we can do this, as we can see by the sketch that I drew out here. Essentially, as a function increases, the slope's also going to be positive. The blue lines are the tangent lines, the black lines the graph itself. So as a function increases, the tangent line, or the blue line, is going to be positive. And so then, once it hits the maximum, at that maximum point, the tangent line, or the slope, is going to be equal to 0. And then after that, the tangent lines are going to be getting increasingly negative. So effectively, even before we look at the first derivative test, we can see that a maximum occurs when the derivative of a function goes from a positive value to 0 to a negative value. And it's that transfer from a positive to negative that actually ends up mattering, or negative to positive. And that's how we can use it to find absolute maximums and absolute minimums. Alright, so here's a quick little example. F of x is x cubed plus 3x squared, and we have to find all relative minimums and maximums. So I've graphed it for you over on the left here, and I've circled the maximums and minimums in blue and marked them with little x's so it's really easy to notice. So we can see that there's one maximum, one minimum. The minimum is clearly at the origin, and the maximum is around where x equals -2. But I'll show you how we can prove that using calculus as opposed to graphically. So first of all, we have to find f prime of x because we know that the minimums and maximums are going to occur when the derivative is equal to 0. So f prime of x is 3x squared plus 6x, clearly. And then we have to set that equal to 0. So 3x squared plus 6x is 0, and you get x is 0 and -2. It's pretty simple algebra there. So then we make a sign chart, which you've probably made in the past in algebra. It should be pretty familiar to you. And when x is 0 and -2, we call these critical values. And they're critical values because, well, that is where the derivative is 0 or does not exist. And that is what we use to find relative minimums and maximums. So we make a sign chart with a little number line there, and we put a -2 and a 0 on it, just as long as they're in order and as long as there's plenty of room between them. And we label the sign chart with an f prime of x because A, it's useful to keep track of it during curve sketching when you have an f prime of x, an f of x, and an f double prime of x so that you know which one you're talking about, and well, it's kind of useful on the AP, so you should really get into the habit of doing that. So when we have the derivative of it, if you have a graph, it's really easy. You notice that before -2, the slope's going to be positive. Between -2 and 0, the slope's going to be negative. And then after 0, the slope's going to be positive once again. If you don't have the graph of it, however, which you usually won't because you'll be sketching the graph, all you have to do is plug in some hugely negative number into f prime of x, and you're going to get, well, a positive, because when you square a hugely negative number, that's going to be a huge positive number, which is going to outweigh the 6x, and so on and so forth. You can pick -1 here, and then an incredibly big positive number here. Anyway, because we can see that it goes from positive to negative at -2, and from negative to positive at 0, effectively, this positive to negative means it was positive, hits 0, and then goes negative. Negative to positive means it was negative, hit 0, and goes positive. So it's kind of easy to understand that there will be a relative maximum at -2, 4 and a relative minimum at 0, 0. Here's something you need to be careful of. You need to make sure that it goes positive, negative, or negative, positive. Because let's take an example like g of x is x cubed. I've graphed it for you here. There is a horizontal tangent line at the origin 0, 0, but you can see there's no minimum or maximum. So when you do the first derivative test, you take g prime of x is 3x squared, and you set that equal to 0. X is clearly 0, and so you can say g prime of x, you have the number line with the sign chart, and even though 0 is a critical value, because it's positive on both sides, there is no minimum or no maximum. And we can clearly see that with the graph. So you always have to make sure that it's going to go from positive to negative or from negative to positive if you're going to deduce that it has a minimum or a maximum. That is something that people love to trip you up on. So let's see how this relates to optimization. So you're working for a company that wants to design an open box of side length with a square base of side length x and a height h. So because it's an open box, you only have to worry about 5 sides as opposed to the regular 6. So they give you the surface area and they tell you, all right, we want the surface area to be 108. And so you know by your handy dandy math notebook that that is going to be x squared plus 4xh, because the x squared is the base and then 4xh is going to be each of the sides. And you also know that the volume is going to be x squared times h. And your goal is to maximize the volume with only a surface area of 108. So, first we need to figure out what a feasible domain is going to be. And we know, well, x can't be less than 0, because you can't have a box with negative area. It's just impossible. And you know that x can't be greater than the square root of 108, because if we go back to the original equation, if, let's say, h is 0, the absolute smallest that it can be, that means that x is going to be the square root of 108. Now we know x is definitely not going to be, well, x is going to be way less than the square root of 108, because if x were to actually be the square root of 108, we would have a really flat box. So, step 2. If you have more than 2 variables, in this case we have a v, an x, and an h, then you need a secondary equation. Beforehand, that v equals x squared h, that is our primary equation. And the equation for the surface area, that's our secondary equation. So what we're going to do is we're going to use that to help us define h in terms of x. I've already done that for you. To make it simple, I just subtracted x squared and then divided by 4x. So h is 108 minus x squared over 4x. Now we can plug that into our original equation to get the volume is x squared times the quantity 108 minus x squared over 4x. So the volume is effectively 108x minus x cubed over 4. So that is our new primary equation. So because of what we've learned with relative minimums and maximums and the first derivative test in general, and just because we're on this topic, I'm pretty sure that you know we're about to differentiate this, which I've already done for you again. And dv dx, or the change in volume with respect to x, is going to be 27 minus 3x squared over 4. And we're going to set that equal to 0, and that's step 3. So, continuing on with step 3, we now have to solve for x when it's equal to 0, which is pretty easy and quick. X is plus or minus 6. But remember, when we limited the domain, the reason we did this is to eliminate erratic numbers. And so we can see that negative 6 is definitely outside the domain, because you're not going to have a negative side length. So we only have to worry about x being 6. So once again, we do the first derivative test. I wrote it as dv dx. You can also write it as v prime of x. And in this case, 6 is a relative maximum because the slope is going to be positive before 6 and negative after 6. You can see if you just plug in a 0 for x here, it's going to be positive, and then if you plug in some huge number for x, it's going to end up being negative. So there is a relative maximum at 6, but that's not the end of it. One would think it's the end of it, but it's not. Because the problem is, because of our domain, we know that there are going to be a couple of endpoints. And that's why step 5 is to evaluate the endpoints. Now, even though you're already super smart, and so you've probably already figured out, maybe because I have it written down, that 6 is going to be the value that we want, you need to evaluate the endpoints, because even though it doesn't work for this problem, in another given problem, I could have a graph that looks something like where it starts here and then goes down and then has like a tiny little relative maximum, then it goes up again, so that the endpoints are actually larger than the relative maximum is. Of course, that's not the case here. The endpoints at 0 and square root of 108 are both 0, and 6 is going to be 108, so that's clearly going to be the maximum value. But you always want to evaluate the endpoints just to be sure. And then, step 6, we are almost done, is to get the dimensions. And so, we know that x is going to be 6, because that's our maximum value, v of 6. And so then we plug that into the original surface area equation in order to get the h value that we want. And so 6 squared plus 4 times 6 times h is 108. So we get 24h is 72, h is 3. So the volume is going to be 6 by 6 by 3. Because we have a square base, so that's 6 and 6, and then the height's going to be 3. And that's 108 for the volume. And those are your dimensions. That is going to be the largest possible box you can make with a surface area of 108. And that's going to be minimizing costs to your company while maximizing profit for exports. And that is why we use optimization and the first derivative test. So essentially, the first derivative test is going to be able to tell you where any sort of maximums or minimums are, and then that can be used in optimization in order to, well, optimize whatever you're looking for within some sort of certain dimension. Just to reiterate a certain point that we didn't really go over that much in this lesson, is that when you have more than 2 variables, you want to make sure that you have a secondary equation. If you have more than 3 variables, you want to make sure you have a tertiary equation. So that is something that you always need to look out for, because people are always going to be trying to trip you up with optimization problems. But if you just keep a cool head, then you'll be able to get through it really quickly. Optimization problems are a lot of fun. Cool. If you have any questions, leave them in the comments. I'll do my best to answer them. And let me know what else you'd like to see. Thank you.